Hello, everybody. Thanks for coming to my talk. My name is Daniel Balsom. I'm the author of the MartyPC emulator, if you've ever heard of that. But today I have a slightly different talk, talking about controlling Intel CPUs with microcontrollers. And the first question I have to answer is, why would you want to do that? The first reason, it's fun. It's a fun project. If you've looked at Ben Eater's series on the 6502 breadboard project, very popular. If you don't have an entire kitchen table to dedicate to sprawling breadboards, this is a much more compact way to do a similar thing. It's also educational. If you've ever wanted to know how a CPU really works, then learning how to control one is a great way to find out. But the third reason, and the one that motivated me, is since I was an emulator author, I was wanting to see if I could improve my emulator's emulation and emulation in general, using some techniques we can do with this. So around 2022, I was scrolling Vogons, and I found this post. The gentleman by the name of Fix, who's now a good friend of mine, he was asking if there were any CPU verification programs that he could run to test his emulator. He was working on an emulator called Virtual XT. And unfortunately, there weren't any. So I kept scrolling, and I found this follow-up post. He made a passive PCB where you can plug an 8088 into the GPIO pins of a Raspberry Pi. And I thought this was absolutely ingenious. The idea is that he would compile his emulator for the Raspberry Pi, and then when his emulator would run an instruction, it would run the same instruction on the physical 8088 and then compare the results. So he knows his emulator is accurate, or it stops. So of course I shamelessly stole this idea. But my emulator didn't run very well on the Raspberry Pi, so I got frustrated with Rust libraries for GPIO on the Raspberry Pi, so I ended up moving over to using an Arduino. These aren't the only projects that have done this. This is Homebrew 8088's Pi 86. It's almost the same thing, really, just a passive PCB connecting to a Raspberry Pi. But there's some more advanced projects, like this is 8-Bit Force's Retro Shield. You can get different shield adapters for your Arduino Mega, and you can connect everything from the 6502 to the 8088. So I'd give those guys a shout out. If you're going to control a CPU with a microcontroller, you've got a lot of options, right? You got the $5 ESP32 up into the very expensive Arduinos and BeagleBones and Raspberry Pis. I ended up using an Arduino for a few different reasons, but if you weren't going to use an Arduino, I might suggest the Pi Pico because it has a very interesting programming model called PIO. It's actually probably more suited for this sort of thing. And some of the more astute among you might be asking, why aren't you using an FPGA? It's kind of the exact thing that's made for this sort of thing. If you take apart an Intel ICE, there's a bunch of FPGAs lurking inside because that's the best way to talk to a CPU. But the main problem is that it's a significant learning curve. You usually need to know Verilog or VHDL, and I don't know either of those. So the best product is the one that you can actually complete. And I think it's very cool that if you can code in C and you can plug some wires into a breadboard, you can control a CPU. It's a project that anyone can take on. And it requires surprisingly little electronics knowledge. But if you are interested in FPGA-based chip control, here's DocTB's Universal Chip Analyzer, and it's got shields from everything from the 8088 to the 46DX2. So there was also the point that there was no reason for me to learn how to do FPGA programming because somebody's beat me to it. So let's talk about GPIO. What is it anyway? GPIO stands for General Purpose Input and Output. And it's the way that microcontrollers communicate with the outside world. You can see the highlighted black plastic headers there are the GPIO pins on the Arduino Uno. An input pin can read a voltage level and give you a 1 or a 0. An output pin, you give a 1 or a 0, and it drives a certain voltage level. And you can switch GPIO pins between inputs and outputs, which sometimes is necessary because many pins on a CPU are bidirectional. And if your CPU ever leaves a pin tri-stated or floating, you can use a pull-up to give it a well-known state. So this is the simple concept here. We're just connecting the CPU's output pins to our GPIO lines and setting them as inputs and vice versa. And that's really literally it. Of course, then we have to write the code that talks to it. There is one electrical consideration that I'll cover, and that's the voltage level. So your older Arduino AVR-based Arduinos were 5 volts native GPIO, so you could talk to a 8085 all day long if you wanted to. Newer microcontrollers have switched almost exclusively to 3 volts. If you connect your 5 volt 8085 to your Teensy, you will immediately destroy it. So you need to do some level shifting, or you can try to see if the CPU will tolerate being undervolted, which many of them will. In the middle, though, we have the PiPicos and the Arduino Giga, and these are 3 volt native microcontrollers, but they're 5 volt tolerant, and tolerant just means you can feed 5 volts to their GPIO inputs and they don't let the magic smoke come out. So I went with the Arduino Giga. I like the footprint. You'll see why in a minute. But it's also got some nice advantages. It's got a 480 megahertz Cortex M7 STM32 CPU. It's got tons of GPIO. It's got 76 digital output pins, of which 70 can be connected to 5 volts. It's got 8 megs of SDRAM. Now you can add SDRAM to most microcontrollers, but this has it built in and it's nice. So what we can do is give the host CPU that we're going to talk to its own address space. It's got flash, it's got a host USB port. Like you could theoretically plug in a keyboard, and I don't know what you do with that, but it's also got built-in Wi-Fi. So the disadvantage is it's kind of pricey, compared to your $5 ESP, it's $70. If you're comparing it to like a Raspberry Pi, it's pretty competitive these days. So some CPU conventions, specifically Intel CPU conventions, we've got a clock line. If we don't toggle the clock line, nothing is going to happen, so that's very important. We have a reset line. Surprisingly, the CPU does not start running the moment you apply power to it. You actually have to reset it with the reset pin. It's like pulling the ripcord on your lawnmower. It's got a ready line, so we can use the ready line to pause the CPU, so to speak, in the middle of a bus transfer. If ready is not asserted, a bus transfer will never complete. It will just sit there and it will insert wait states. We have address pins and data bus pins, and you'll notice on the 8088 here that these pins overlap because it was a multiplexed bus, which is fun to deal with. And there's various bus signals. The 8088 in maximum mode doesn't do direct read and write signals. It has a 8288 bus controller that goes with it, and these are how it communicates to that bus controller. And there's bus mastering pins for the floating point unit and other things that we won't cover. So there's 3 ways to cycle the CPU. Strategy 1 is what I call cycle stepping, and that's simply we're going to take the clock pin, the GPIO line that's tied to the clock pin, we're going to set it high and we're going to set it low again. That's clock. The advantage of this technique is you can see and control every CPU cycle, right? Because you're deliberately clocking the CPU one time. And you can potentially undervolt the CPU because you're clocking it so slowly. Like the power draw of a CPU is like proportional to the frequency. The disadvantage is it's slow. Even on the Giga, I don't get above 200 kilohertz doing this. And this requires a CPU with a static core, and what that actually means I'll cover in a minute. So strategy 2 for clocking, we could generate a square wave on the GPIO clock output pin using like the PWM mode some GPIO pins have. Make a simple square wave. Or even better, a hardware timer, because you can clear the timer to even like tweak the duty cycles and such. The Arduino Giga can easily do a 66 megahertz square wave using a hardware timer. The idea here is that our microcontroller is probably not fast enough to keep up to a natively clocked CPU, so we're going to arbitrate the ready line. We keep the ready line low, and so we wait for a bus transfer to be sitting there doing wait states. Then we write the bus and set the ready line high again, and then we hopefully have a hardware interrupt on like the ALE signal to draw that ready line low. This is fast and it supports every CPU, even older NMOS CPUs, because you're ticking them at their native, documented rate. but the cons is it's more challenging to code. And it starts to require actual electronics knowledge. You can't really run a 66 megahertz clock through a breadboard unless you know what you're doing. But you may not see every CPU cycle because there's going to be potentially hundreds of wait states while your Arduino is waiting to catch up. Being an emulator author, I was only interested in exact cycles of what is going on the CPU, so this disqualified this technique. Strategy 3 is simply, you could use an external crystal or clock generator board and tie it to a GPIO pin and have a hardware interrupt on that. The only reason you want to do this is like if you wanted to emulate an XT on your Arduino with an 88 CPU, you would give it that specific NTSC-derived 14.318 megahertz clock. Other than that, same pros and cons of strategy 2. So we're using strategy 1. And so I need to talk about dynamic logic a bit. Early microcontroller CPUs use the NMOS process. It means N-channel metal oxide semiconductor. And the best way I can explain this is that dynamic logic is where they exploit capacitance in the circuitry of state. You have gate and stray capacitance. And instead of being a problem, they utilize this to store info. But like any capacitor, the charge will dissipate over time very quickly. So what happens is these chips have a minimum clock. Like the 8088, you have a minimum clock of 1 megahertz for the NMOS model. And if you don't give it that minimum clock, it does weird things. It appears to function, it fetches opcodes, it puts addresses on the address lines, and then it just completely fails to add two numbers together. It's a bit of a problem. But we have some good news. In the 80s, people started moving to CMOS processes. Some of the second source providers for Intel were specialized in CMOS CPUs like Harris. So there's less reliance on dynamic logic for a CMOS CPU. It's not always no dynamic logic. But if you get lucky, you can get a fully static core which has no minimum clock rate. You could literally clock it once a week and the chip will continue to function and remember what it was doing. So this table here is all the CPUs that I've successfully operated as CMOS parts. So you have 4 generations of Intel CPU you can play with. So here's some simple code to clock the CPU. I've replaced the digital write function because there's a lot of boilerplate in that function and it's kind of slow. We've got a macro now that'll do direct GPIO port manipulation. But we're just calling that macro to set the pin high and then set the pin low again, and tick CPU gets called in our loop, and then the loop function gets called as fast as possible by the microcontroller. And that gives us an 8.33 megahertz square wave on the Arduino Giga, which is actually too fast if we were going to play with a 5 megahertz 8088, right? We don't want the high portion of the clock to be too skinny for the CPU to recognize it, so we need to slow down a bit. And we can do that by inserting a spin loop. We don't use a sleep or anything because there are no sleep primitives that can do nanosecond resolution. So we just spin loop 3 times, and that stretches the clock out just enough that now we're down to 4.55 megahertz. There's no like Goldilocks number. If you do 3, it's a little too slow. If you do 4, it's a little too fast. But once we can clock the CPU, the next thing to do is to reset the CPU. And to reset the CPU, we simply assert the reset line. And whether this is like logic level high or low depends on the CPU. Intel kept changing this for some reason. And then we clock the CPU the requisite number of times. You just look it up in the data sheet for the CPU you're working with. Then we deassert the reset line and we keep clocking it. And it's going to run a microcode routine called reset. And this was varying lengths for different CPUs. As generations got on, the reset procedures went longer and longer. But eventually, you should see something happen. I know this is a little hard to read, but down at the bottom, we have an address line readout, the data bus, some bus signals, and then the decoded bus state. So we see an address of FFFFF0, which is the x86 reset vector. It's always 16 bytes from the end of memory, and that just gives you enough time to do a far jump into your BIOS startup code. We can also see that that's a code fetch, so that's a good sign, right? The CPU, the first thing it should do after it's reset is start fetching code. So now you're off to the races, and you can just operate the CPU. And I've got to skim over a lot of details that would take an hour by themselves on this one slide. But the idea is when the CPU is asserting a read signal, we're going to simply write a value to the data bus, give it something to read. And when it's asserting a write signal, we're going to listen to it and read that value from the data bus, put it somewhere, either in memory or a hash table. When operating a 16-bit bus, though, we have a little more difficulty because the Intel 16-bit bus is an odd even arrangement, and so we have this BHE pin, and along with the A0 line, that determines which halves or both halves of the data bus are actually driven. So it's a little more complicated, but not too hard. There's another fun thing we can do. If the CPU is emitting code fetches, we don't even have to emulate memory. If we have a stream of code we want to run through our CPU, as long as it doesn't jump anywhere, just feed it every opcode in order. You don't even have to care what the address is, because it's just going to fetch it and run it in order. So it's very relocatable. But if you do want to have variables or do want to do some jumps, you can emulate memory with a hash table. If you have a low memory microcontroller like Arduino Mega has something sad like 4K of RAM. And the Arduino Giga can map all our reads and writes to our 8 megs of SDRAM, so that's awesome. So you've got this microcontroller and it's controlling a CPU and it's doing stuff and maybe logging some stuff internally, but it would be useful to get that off the microcontroller into the real world somehow. So we could always plug in an LCD or OLED display. There's a lot of little cute displays that go right into your microcontroller pin on like the I2C bus. You can write it to flash or an SD card. You can send data over a serial UART. I use this for my debug channel. And then you can send data over USB. The Arduino Giga has a USB CDC connection. So this single cable is both power and what I use to communicate with the control board. But if you have Wi-Fi or an Ethernet port, you can also use TCP/IP, and maybe that would have been a better idea. Like the Teensy and the BeagleBone have like physical Ethernet ports. You have to solder it on the Teensy. And you have Wi-Fi on the Pico W and the Arduino Giga. So I recommend building a client-server model with your Arduino or your microcontroller. The server, I call it the CPU server, runs on the microcontroller, and the client will run on the host PC. Client sends commands to the server. So we're just defining a protocol here. And you can send commands like read the address latch, write the data bus, read this pin. And can't read all that, but that's all the commands that I've currently implemented in my CPU server. And then once the command is executed, it's going to send the results back to the client. So here's my first breadboard. I had connected an 8088 to a Arduino Mega. And this was operating in maximum mode. So I had the 8288 bus controller there over on the right. The orange lines are the CPU's bus status pins going over there. And the little red wire is connected to the ALE pin. That's the address latch enable pin, and that goes high for one cycle when a bus cycle begins. So when that lights up, you can see there's a bus cycle starting, which is kind of neat. But I didn't want to have a messy breadboard, really. I had envisioned a shield that I could stick on top of the Arduino like a Raspberry Pi hat. And I had never done this before, but it turned out to be a lot easier than I expected because we have KiCad. This is a free open source CAD PCB design software. You just download it at that website, and it does everything you need. And then once you've designed your PCB, you can ship it off to any of these PCB manufacturers, and they'll turn it around for you like in under 2 weeks at a ridiculously low price. So here's what my 8088 shield looked like in KiCad. First PCB I ever designed, and I look at it now and I cringe a little bit because there's a lot I would have done differently, but it worked. And this is what I got back from PCBWay after about 2 weeks. And it is really cool holding a PCB that you designed in your hand. Like, the fact that this doesn't cost thousands of dollars to do will always amaze me. I got 10 of these boards made. It cost me $5. Not per board, $5 total. The shipping was like $22, but still. So here it is with some sockets installed. I sprung for this expensive $8 ZIF socket. It's got the little lever on the left because I was experimenting with a lot of CPUs, and every time I pull a DIP40 CPU out, I bend one of the pins. So this was sparing my poor suffering CPUs from further damage. And this is what it's running. It's got an NEC V20 in it, and I've got my RS-232 board connected to the serial debug UART so I can see it'll print out every cycle of the CPU what it's doing as kind of a debug channel separate from the client server channel. So, well, this actually worked really well. I was able to accomplish my goals, validate my emulator, run Area 5150, publish 8088 CPU tests that over a dozen emulator authors have used to date, which I'm extremely proud of. But then I started thinking, if these tests are so useful, it would be nice to have tests for other generations of CPU. So here's the 186. It's not as famous as its brother, the 286. They were released at the same time. The 186 was designed for the embedded market, although some PCs were built around it, like the Tandy 2000. We have CMOS variants available. Like this is an AMD 80C 186, so that's probably, you could cycle step it. It's no longer a convenient DIP package. You can see it's in a PLCC68 socket. And it's a 5-volt chip that, in my original experiments, didn't like being undervolted. But then I found this guy. This is the 80L186. Intel kept making the 186 like well into the 90s. And this is one of the later revisions. You can see how small it is. It's a fully static core now. It's 3 volts, so you can use any microcontroller you want. But it's a surface mount component. My soldering skills were really put to the test here. So you can get this breakout board, and then you stick it on there very carefully, and you say a prayer to the Hacko gods and do your best drag soldering attempt. But it actually worked. I was able to wire up a bunch of messy wires and plug them in, and I was able to run code on the 186. And I was about to make tests for the 186, but then I realized nobody wants tests for the 186. They want tests for the 286. They only would take tests for the 186 because there are no tests for the 286. So let's just make tests for the 286. Again, the 286 has CMOS variants available. Here's a Harris 80C286. So that's a CMOS version. But it's still that annoying PLCC68 socket. And it's still only 5 volts. But it was about this time that I discovered the Arduino Giga was 5-volt tolerant, which changed everything. And then I found, shortly after, this PLCC68 to DIP68 adapter made by ChipQuick. It's a little pricey. This guy's $18. But what this lets you do is breadboard a 286. So this worked as well. I was able to make 286 tests for emulator authors. I'm in the process of designing a PCB for it. We've got the PLCC socket here in the center. There's 2 helper chips, the 82288 and 82284 on the left. And I was trying to add a 287 FPU on the right, which I think I'll drop because it's just, well, you'll see in a second. So once I got the 286 working, I was getting mad with power, and I thought, let's do the 386. The main problem with the DX is it's got a 32-bit address bus and a 32-bit data bus, and yes, it is address line 31 for the FPU. That's too many pins, right? Most microcontrollers have run out of pins at this point. It's also not fully static. Intel was moving to a CMOS design, but they never claimed that there wasn't a minimum clock for these chips. There was no guarantee it would work. But Intel later made the Intel 386EX. I don't know if any of you have heard of this chip. It was designed for the embedded market. If any of you have owned a Garmin Street Pilot GPS unit, there was one of these powering it. And it's cool because it's got a 16-bit data bus like a 386SX. And it's fully static, and there's 3-volt versions available, but even the 5-volt versions run fine at 3 volts at the low clock speeds we're giving it. Intel had learned their lesson from the 186, and now all the peripherals are AT compatible. So you can actually, other than needing to add a keyboard controller and CMOS memory, you could probably boot to DOS with this thing's hooked to an Arduino. I'm still working on it. The main con is, look at it. It's got 138 pins surface mount. So there's no commercial breakout board. There is a breakout board you can order on PCBWay's website. Somebody upload one. But if you're going to wait 2 weeks for a PCB to get shipped to you, you might as well make your own. So here's what I did. This is a little more complicated than the 8088 board, but it's still the same idea. I'm not an electrical engineer. I had no background in PCB design. I'm just putting wires down and making them look pretty. And then I pray that it works. So here's the PCB I got. This was ordered from Osh Park. They specialize in purple, so that's nice. And here it is. And here it is. And I'm going to be giving a demo of it right now. It actually works. So all my code, I call this project Arduino x86 because I called it originally Arduino 8088, but then I outdated my name. And if you like that little mascot, I've got a ton of stickers of him. Some come find me after the talk. But all the KiCad files, all the PCB shield designs, all my code for everything is at my GitHub right there. If you want to take this project on, feel free to reach out to me. I'd be glad to help you with it. So let's do a quick demo. So I cheated and already connected to it, but it says here that we're connected to an Intel 386, so it knows what CPU we're talking to. This window here is in our initial register state, so we can actually set the registers to anything we want before we run any code. The way that works is that the 386 has a load all instruction. This was designed for use by operating systems, but we're abusing it to just set the register state as soon as we reset the CPU. And I can upload the registers. There, I can upload the registers. I have the right options toggled. So this is actually a cycle that is just executed. So if you notice, our CS was 1000, our IP was 100. So now we're starting at address 10,100. If you know how segment math works, that should check out for you. And we've got this data bus. And notice this is an edit field. Anything I type in here is immediately set to the data bus pins of the CPU. So I've got 9090 in here. Some of you probably know 90 hex is a no operation. So I can just keep feeding it. I'm literally clicking to clock the CPU. And you'll see that all it's going to do is fetch NOPs and execute NOPs, which isn't very exciting. But if we look at how often it's doing it, it's every 12 cycles. The 386EX, even though it has a 16-bit data bus, it's still a 32-bit CPU, and it's going to fetch 32 bits at a time. But it has to break it up into these two separate 16-bit code fetches. So it's fetching 4 NOPs every 12 cycles. That's 3 cycles per NOP. Checks out again. It's pretty cool. One thing is a little ridiculous here is if I wait till T1 of a code fetch, oops, missed it. I got the jitters. I can actually edit the data bus now, and I can feed it all zeros. 0000 is an add instruction using a memory operand. And so I just fed it 2. If we keep going, now we should soon see it start to execute a memory bus cycle. So now it's executing the add instruction. There was such a delay because the 386 has a very long prefetch queue. But notice the address that the memory read occurred on is 0 because all of our registers that we used for the address calculation are also 0. If we keep toggling, we'll see the memory write to the same address. So you can like literally manually operate a 386. I think that's pretty cool. But writing machine code is not everyone's cup of tea. So we can do assembly language. Everything you write needs to end in the halt so that it knows when to read the register state out. Let's write a simple program. So I'll move 1 into AX, 2 into BX, and we'll, if I can type, add AX and BX together. And I can assemble this. Oh, I misspelled move. Oh, yes, thank you. What would I do without you guys? So this gives us a 9-byte binary. And notice we can mount this at CSIP or use a specific flat address. Usually want to leave it on CSIP, so whatever register you've set, it'll run the program right there. Everything good there. So that gives us all the cycles for our program. And you can copy them out and save them and research them. But we can also look at our final register state. The registers that changed are highlighted in cyan, so we can see that our result is actually 3. Check my work. So that's neat, right? We can even, there's no limit here. So let's take our result and output it on an I/O port. So now if I move the register window out of the way, you'll see these I/O write bus cycles. Now the actual write just takes a single cycle here. The 386 is messy. It doesn't clean up after itself with the bus state. It just leaves the bus state on there, even though there's no bus transfer in progress. Makes it a little hard to follow. Makes this look like this I/O write took forever, but it really was only 1 cycle. So we can run more advanced stuff. And let me get rid of this program. Some of the guys on the size coding Discord, the demo scene, helped me out making some examples for this demo. This is by a guy named Plex, and I'm going to turn off cycle logging and run it. So how do we see anything? It's doing something, but over here in my memory viewer, I have an address of A0000. Some of you might recognize that address as being the VGA graphics frame buffer. But I have this, I took the memory visualizer out of MartyPC, which I used in my talk last year. And we can come over here and tweak some values. We've got our little arbitrary resolution VGA screen. So that little demo effect is in 93 bytes. I've got another one. need to make this a little bigger. So this draws a cool fractal. So you can see you can actually run useful code on this thing. It's not just a toy. I got one final demo to show you. This is the most complicated thing I run on this thing. This is a 32-bit Mandelbrot generator. Oh, this fractal demo was made by Helmut, by the way. Some of you might know him. He's a very famous size coder. So here's a complex Mandelbrot. It does 16 by 16 fixed point math. I'll build him. Oh, I'm looking at the wrong thing here. Sorry. I made all the windows bigger so that you could see them, but now I'm trying to find everything. No, it's up here. That's a bit too big. So this is, as you can see, you're probably familiar with what a Mandelbrot looks like. But this is an example. I want to show you the power of controlling a CPU. I can edit the code and re-upload it while the program is running. So for example, I can change this color offset that was set to 32. I can set it to 64. This is just the number that's added to the final iteration count to select the VGA palette index. Now I just have to find my binary window. So what we should see is that the Mandelbrot starts rendering in a different palette, keeping the same, temporary variables and everything. The trick to that is you want to put your variables in the BSS segment so that they don't get outputted as zeros in the binary. Otherwise, when you re-upload your binary, you'll reset all your variables. But I think that's kind of a neat concept that you can modify code. You have to be careful with like instruction boundaries. You don't want to you don't really know where the CPU is fetching. If you disrupt the instruction boundaries, you could generate an illegal instruction. And now you're in the middle of int 6. And I don't have an int 6 handler, so it's probably just going to triple fault. But while we watch this render out, does anybody have any questions?
Super impressive. A quick question for you. This seems to be like a great platform to actually build like a 2 or 3 chip entire system. Because with something like PIO, you could probably get a display and peripheral control, and then pretty much that's the only other thing you would need on the board. Have you thought about that?
Yeah, and in fact, the Arduino Giga has a Giga display shield. The sad thing is that it has almost no power budget after you've plugged it into the shield, and it can't power the 386 and the shield at the same time. And you say, well, why don't I externally power the 386? I don't know if you can see this. This is the external power pin to the 386 VCC pins. You notice there's nothing connected. That's an interesting artifact of CMOS process CPUs. They will power themselves by any pin. So I literally have no power going to this chip other than like the address and the data lines. As long as one pin is high, the chip's good to run, at least at this low clock speed. So I can't turn it off. I can't the Arduino is going to feed it power no matter what I do, just by the nature of the GPIO pins being connected to it. It's like parasitic. I don't know what the right term is. But I'm sure there's ways you could buffer or something that, I mean, like I said, I don't have a lot of electronics knowledge, but it would be really awesome to get the display working. And you could plug in a keyboard, have a little full AT system.
Yeah.
Very slow AT system, but
Nice. Thank you.
So, how are you seeing people use this so far with basically the tests you've created or like outputs of this work that you've done?
yeah, the most constructive output of this project has been the CPU tests that I've made. I built this GUI very recently, pretty much so I would have something more interesting for you all to look at than a bunch of cycle traces. But I am planning, and I'm working on right now, generating CPU emulator tests for the 386. It's just a lot more complicated. When you add 32-bit opcodes, you take an average random 32-bit number, and then you try to fit it into a 64-bit segment. Like 99.9999% of the time, it's going to be bigger than 64K. So it's just like every instruction you generate is a GPF. So I've had to do a lot of work on masking everything to the segment limit and generating not random but useful bit patterns instead of random numbers. I had to write a whole 386 decoder so I could calculate the addressing logic with the mod_rm and the SIB byte for the 386, so I could patch the indirect memory operands for things like jump and call indirect. But I'm so close. They'll be out by the end of the year. And then I get to work on protected mode. And I know like people are like, well, don't DOSBox and 86box already have 386 emulation that's rock solid. And yeah, but the main idea is that it's like the demo scene in a way. People are constantly writing new emulators as a hobby. So this is for future emulators that have not been written yet. Like maybe I'll write a 386 emulator one day and I'll use my own tests. I'm just trying to improve the emulation world, in some small way, I suppose. All right, well, thank you, everybody.